Listen, it is May in Detroit, 1936, a season where the air should be thick with the promise of industrial rebirth. But inside the General Motors research laboratories, the atmosphere is as cold as a morgue. Outside, the spring blooms are pushing through the Michigan soil. Yet inside these walls, the future of American transport is quite literally cracking under the pressure. The pride of the fleet, the Winton 201A diesel engine, was supposed to be the silver bullet that finally put the steam locomotive in a museum. But instead, it has become a punchline in the smoky roundhouses from Chicago to the Gulf. Every time a streamlined passenger train roars past a siding, the engineers on the steam locomotives laugh, knowing that beneath that sleek, Art Deco stainless steel skin, the Winton is a ticking time bomb of metallurgical failure. It is a machine that can handle the vanity of a high-speed passenger run, where the load is light and the glory is high. But the moment you hook it to a mile-long manifest of coal and steel, it begins to devour itself. This is the buried secret of the early diesel era. The revolution was stalling before it even cleared the yard. The aluminum pistons, light and fast for the race to the coast, are disintegrating every 50,000 miles, turning precision engineering into jagged scrap metal. The crankshaft bearings, designed for the steady hum of a laboratory, are fracturing under the brutal, shuddering torque of heavy freight service. By this mid-May morning, the ultimatum from the boardrooms of the great railroads has become deafeningly clear. They don't want a fashion statement, they want a beast of burden that can survive the Appalachian grades and the Mojave heat without a mechanic holding its hand every 100 miles. General Motors didn't just have a mechanical problem, they had a crisis of identity. If they couldn't solve the diesel's fragility, the company would be forced to retreat from the rails, leaving the empire of iron to the coal-fired giants of the 19th century. The failure was so pervasive that many in the industry believed the two-stroke diesel was a dead end, a theoretical dream that couldn't survive the grease and grit of reality. But as the spring rains wash the soot from the windows of the Detroit lab, one man is staring at a blank sheet of paper, preparing to make a choice that most corporations would consider institutional suicide. Eugene Kettering knows that you cannot patch a fundamental flaw with hope and half measures. To save the future, he has to be willing to bury the present. The 201A was a pioneer, but pioneers often die in the wilderness, and Kettering was done wandering. He wasn't looking for a tweak or a modification. He was looking for a replacement that would render every other engine on the planet obsolete. The pressure wasn't just coming from the balance sheets, it was coming from the very legacy of his father, the legendary boss, Kettering. This wasn't just about moving freight. It was about proving that the modern world belonged to the internal combustion engine, no matter how many tons of steel the railroads demanded it haul. The stakes were nothing less than the total dominance of the North American continent. And as the clock ticked toward the summer of 1936, the team in Detroit began the desperate work of building a legend from the ground up, starting with nothing but a mandate to succeed where everyone else had failed. The boardrooms at General Motors were not places for sentiment, and by the late 1930s, the accounting department was seeing red every time the word railroad was mentioned. Millions of dollars had been poured into the Winton Engine Corporation, yet the returns were coming back in the form of cracked cylinder heads and warranty claims that threatened to bankrupt the vision of a dieselized America. As the biting winds of late autumn 1937 began to rattle the windows of the LaGrange facility, there was a palpable sense of dread among the shop floor supervisors. They were tired of seeing the same locomotives return to the bays just weeks after being fixed. The 201A was becoming a reputational albatross, and the old guard steam advocates in the industry were smelling blood in the water. For decades, companies like Alco and Baldwin had built their empires on the reliable, clanking simplicity of external combustion, and they were more than happy to watch General Motors choke on its own complexity. Inside the LaGrange plant and the Detroit labs, the politics of the New Deal for railroading were brutal. Eugene Kettering had to navigate a minefield of internal skepticism where every dollar spent on a blank sheet design was a dollar taken away from trying to salvage the existing product line. The pressure wasn't just coming from the bottom line, but from the clock. The railroads weren't going to wait forever. They were already looking at high-pressure steam and experimental turbines as alternatives to the temperamental diesel. Kettering's team was operating in a pressure cooker of engineering dogma. The decision to abandon the 60-degree V-angle of the Winton wasn't just a technical choice. It was a political statement that the old ways were fundamentally broken. A 60-degree engine was balanced, sure, but it was a bloated, wide body that couldn't fit into the narrow, road switcher silhouettes that forward-thinking designers were already sketching on their pads as the 1938 production season loomed. By forcing the engine into a 45-degree V, Kettering was inviting a nightmare of vibration and secondary balance issues that his team had to solve with sheer mathematical violence. They weren't just fighting physics, they were fighting the clock and the pervasive fear that if this engine failed, General Motors would be forced to exit the heavy industrial market entirely. The workshop was a landscape of discarded prototypes and failed castings, a graveyard of ideas that weren't tough enough for the high-tonnage world of freight. Every night, the lights in the Detroit lab stayed on long after the streetcars stopped running, as engineers obsessed over the thickness of the steel plates for the crankcase. They were moving away from the elegant, lightweight castings of the aviation-inspired 201A and toward a rugged, welded steel philosophy that looked more like bridge construction than engine building. This was the industrialization of the diesel, a transition from a delicate instrument to a sledgehammer, and the cost of being wrong was the death of an entire division. As 1937 bled into 1938, the financial stakes shifted from risky to existential. The Great Depression was still casting a long shadow over the American economy, and the railroads were not in the mood for expensive experiments. They needed a machine that could pay for itself in fuel savings and reduced maintenance within the first 3 years of operation. Kettering knew that he couldn't just produce an engine that worked. He had to produce an engine that was indestructible. The shop politics of the era meant that the mechanics in the field, men who were used to hitting things with hammers to make them work, had to be won over. If the new engine required a PhD to maintain, it would fail in the dirt and grime of a Montana winter. The mandate was clear: make it modular, make it accessible, and for God's sake, make it stay together. The team was working under a veil of extreme secrecy, knowing that any leak of their struggles would be weaponized by the steam builders. There was no room for ego, only the cold, hard logic of the test stand. When the first prototype of what would become the 567 finally roared to life, it didn't just sound like an engine. It sounded like a declaration of war against the status quo. But the sounds of a successful test in a controlled lab were a far cry from the realities of the high plains. And as the 1938 deadline approached, the team realized that the hardest part wasn't designing the engine. It was convincing a skeptical industry that General Motors had finally built a diesel that didn't have a glass jaw. When you peel back the steel skin of a 1938 EMD, you aren't just looking at a motor. You're looking at a structural rebellion against the limits of metallurgy. The 567 was an exercise in obsessive over-engineering, defined by a massive 567 cubic inches of displacement in every single cylinder. While competitors were still struggling with the brittle nature of massive iron castings, Kettering's team abandoned the foundry for the welding torch. They fabricated the engine block, the very skeleton of the machine, from rolled steel plate and forged steel members, welding them into a single, rigid crankcase. This was a radical departure from industry norms that favored heavy, poured iron blocks which, if they cracked under the rhythmic pounding of a mountain grade, were effectively junk. With the 567's welded structure, a railroad shop crew in the middle of a blizzard in North Dakota could fire up a standard arc welder and repair a stress fracture right in the frame, keeping the tonnage moving while the competition's engines were being hauled away for scrap. But the true genius lay in the geometry. By narrowing the bank angle from 60 degrees down to a tight 45, the engineers created a profile that was taller but critically narrower. This narrow waist meant that the engine could be flanked by walkways inside the locomotive hood, allowing a mechanic to access the guts of the machine without dismantling the entire car body. This decision alone would eventually birth the road switcher revolution. But in the immediate term, it meant that the 567 could deliver a staggering 1,350 horsepower in its 16-cylinder configuration, without hogging every inch of internal space. The thermal management of this beast was a masterclass in solving the odd failure modes that had plagued the earlier Winton designs. The 201A had failed because it tried to use lightweight aluminum pistons to shed heat, but those pistons would crown and shatter under the relentless thermal load of a heavy freight haul. Kettering's team went the other way, opting for heavy, floating cast iron pistons that were designed to expand and contract without seizing, cooled by a constant, high-pressure spray of lubricating oil directed at the underside of the crown. They moved the cooling water through a uniflow scavenging system, using a roots-type blower to force fresh air through ports in the cylinder liner, which not only cleared the exhaust, but chilled the internal components between every stroke. It was a brutal, efficient cycle that allowed the 567 to maintain its rated output while lugging a mile of freight up a 2% grade in the suffocating heat of the desert. While steam locomotives were losing power as their boilers struggled with bad water and altitude, the 567 just kept breathing. And then there was the power assembly, the ultimate victory for the shop foreman. In an era where a broken valve often meant a week-long teardown, the 567 was designed for modularity. The cylinder head, liner, piston, and connecting rod were engineered as a single, interchangeable unit. If one cylinder failed, you didn't rebuild the engine, you pulled the assembly out like a spent cartridge and dropped in a fresh one. This meant a two-man crew could perform what used to be a major overhaul in a matter of hours. A feat of field improvisation turned into a standard operating procedure that changed the math of railroad profitability overnight. Every bearing, every injector, and every gear was built to a standard that assumed the worst possible operating conditions, ensuring that when the 567 hit the notch 8 position on the throttle, it didn't just scream, it held. The skeptics were lined up along the right-of-way from Chicago to the Pacific, waiting for the experiment to shatter. In November 1939, a 4-unit set of locomotives carrying the number 103 rolled out of the LaGrange plant, dressed in a humble livery of green and yellow that belied the fury of the 64 cylinders hidden beneath its skin. To the veteran master mechanics of the era, men who had spent their lives measuring power in the hiss of high-pressure steam and the rhythmic clanging of side rods, this machine was an intruder. The prevailing myth of the 1930s was that a diesel could never provide the slugging power required to move a 100-car manifest over the Continental Divide. They were considered fine for the boutique world of passenger transit, but too fragile for the coal-dusted reality of freight. However, as the 103 embarked on its 11-month marathon across 20 different Class I railroads, the records began to expose the fraudulence of that skepticism. The paperwork that filtered back to the General Motors boardrooms was a ledger of absolute conquest. Across 35 states and over 83,000 miles, the FT demonstrator didn't just meet the performance of steam locomotives, it humiliated them. The logs revealed a machine that burned barely half the fuel of a comparable steam giant while hauling heavier tonnage in shorter times. In the arid stretches of the Southwest, where the Atchison, Topeka, and Santa Fe fought a constant, expensive battle to find enough water to keep steam boilers from exploding, the 103 was a miracle of logistics. It needed no water stops and minimal servicing between runs, turning the traditional 4-hour maintenance window into a 10-minute inspection. The witnesses weren't just salesmen, they were the very railroad superintendents who had once laughed at the Winton, and they were now frantically trying to find room in their budgets for the production models that EMD promised would follow. Yet just as the 567 was poised to take over the American mainline, the geopolitical landscape fractured. When the United States entered World War II, the War Production Board assumed total control over the nation's industrial output, and for a moment it seemed the diesel revolution might be frozen in its tracks. The board issued a directive that would eventually be viewed as the most significant reversal in railroad history. They prohibited traditional steam giants like Alco and Baldwin from developing new diesel road locomotives, forcing them to continue churning out the steam technology of the past to meet wartime tonnage requirements. But because the 567 had already proven itself, and because General Motors was a purely diesel-focused manufacturer, EMD was granted a rare exemption. The reason wasn't just about the rails, it was about the ocean. The United States Navy had looked at the 567 and recognized it as the perfect heartbeat for a new kind of vessel, the landing ship tank, or LST. The 567A variant was drafted into service, powering hundreds of these flat-bottomed workhorses across the Atlantic and the Pacific. While those diesels were driving landing craft onto the beaches of Normandy and Iwo Jima, the wartime restrictions back home were effectively murdering the competition. By the time the war ended in 1945, Alco and Baldwin were 5 years behind the curve, left with aging steam designs and unproven diesel prototypes. Meanwhile, EMD emerged from the conflict with a battle-hardened engine and a factory that had spent the last half-decade perfecting the art of mass-producing the most reliable prime mover on Earth. The myth of steam's necessity had been officially dismantled by the 567's record of service, both on the American prairie and the global battlefield. When the restrictions were finally lifted, the floodgates opened, and the railroads realized that while they had been fighting a war, Eugene Kettering's team had been building the future. The transition wasn't a gradual shift anymore, it was a landslide. And by 1947, the LaGrange factory was turning out 4 locomotives every single day, leaving the old steam builders to scramble for leftovers in a market they no longer understood or controlled. The payoff of Eugene Kettering's 1936 gamble didn't just manifest in sales figures. It manifested in an architectural immortality that is almost unheard of in the history of heavy machinery. By the time the GP7 and GP9 began to crawl across the American landscape in the 1950s, the 45-degree V angle of the 567 had become the industry's secret weapon. Because the engine was so narrow, it allowed for the hood-style locomotive that gave crews 360-degree visibility and maintenance teams unprecedented access. It was a design so right that when the horsepower race of the 1960s began, EMD didn't have to throw away their blueprints. They simply bored the cylinders out to create the 645 engine, keeping the same external dimensions so that a 3,000 horsepower prime mover could drop into the same frame that once held half that power. This wasn't just engineering, it was a modular empire. When the 710 followed in the 1980s, the lineage remained unbroken, a testament to a design philosophy that valued evolution over obsolescence. While the legendary names of the steam era, Baldwin, Lima, and Alco, collapsed into bankruptcy or were absorbed into conglomerates, the descendants of the 567 continued to pull the nation's tonnage. The SD40-2, powered by the 645 E3, became the gold standard of the late 20th century, a machine so reliable that railroads today are still spending millions to rebuild them rather than buy something new. Even now, nearly a century after that first sketch in Detroit, the distinctive, high-pitched scream of the EMD two-stroke remains the heartbeat of North American commerce, a sound that has survived the transition from the Great Depression to the digital age. It is easy to look back at this history and see a series of clean victories, but popular documentaries often compress the agonizing reality of industrial development into a convenient narrative of inevitable success. The truth is that for every 567 that left the factory, there were thousands of man-hours spent scraping carbon out of test cylinders, arguing over the thickness of a weld, and sweating through the fear that the next crankshaft might fail in the middle of a desert crossing. The miracle at LaGrange wasn't a single flash of inspiration. It was a decade of brutal, unglamorous persistence by men who were willing to risk their careers on a clean sheet of paper. We talk about these machines as mythic entities, but they were built by exhausted engineers who didn't know if they were making history or just delaying a bankruptcy. The 567 lineage is the rarest of things in our modern world, a tool that was designed so well the first time that its core architecture survived long enough to see the people who built it grow old and retire. It remains the only two-stroke diesel engine family still in common service on the rails, a mechanical outlier that refused to follow the four-stroke trend of the rest of the world. No other prime mover lineage has spanned this many decades or maintained this level of parts compatibility from the first production engine to the last, surviving through mergers, economic collapses, and the total transformation of the American railroad. Today, the original FT demonstrator, Unit 103, rests in the quiet halls of the National Museum of Transportation in St. Louis. Its streamlined nose is polished, its 567 engines are cold, and its work is long finished. But its DNA is still vibrating in the air across the Great Plains and the Appalachian Passes. Every time you see a blue and yellow or orange and black freight train thundering toward the horizon, listen for the fast, rhythmic pulse of the engine. That sound is a direct acoustic link to 1936, a mechanical echo of a team that decided to stop patching failures and start building a future. It is a reminder that in an age of planned obsolescence, some things were built to outlive us all. The 567, 645, and 710 are more than just part numbers. They are the iron spine of a continent, proving that sometimes the only way to truly move forward is to have the courage to throw everything away and begin again with a single, perfect idea. If you've ever stood by the tracks and felt the ground shake as a classic EMD roared past, you know that some machines don't just move freight, they move the very spirit of an era. Tell us in one line, which legendary EMD locomotive model do you believe represents the absolute peak of the two-stroke era?